So when you look up at the sky, our sun seems like this constant, steady presence, right? Well, actually, beneath that blinding surface, it's this incredibly volatile, churning reactor that regularly throws massive magnetic tantrums. The question we're tackling today is a big one. Can we actually predict the violent magnetic storms of our nearest star before they even happen?
And look, we really need to figure this out, because predicting space weather isn't just some fun academic exercise. It's absolutely crucial for our modern tech-friendly lives. When the sun hurls charged particles our way, that space weather can completely knock out multi-million-dollar satellite operations, influence Earth's climate systems, and even threaten global power grids. We're talking about the potential to plunge entire continents into darkness. So the stakes here are, quite literally, astronomical.
Okay, so today we're diving into this absolutely fascinating new research paper by Shanwi Tapala. And honestly, it reads like a cosmic detective story. We're trying to crack the sun's magnetic code. We're going to look at how astrophysicists are figuring out exactly which clues give us the absolute earliest, most accurate warning of the sun's next big move.
Here's our roadmap for this explainer. First, the solar cycle mystery. Then, two cosmic suspects, testing a century of data, the winning predictor, and finally, forecasting solar cycle 25. Let's get into it.
Section 1. The solar cycle mystery. The stakes of our cosmic neighborhood.
Now, to predict the sun's behavior, we first have to really understand its rhythm. And since you follow this stuff, you already know the sun operates on a roughly 11-year cycle. We track this heartbeat by counting sunspots. You know, those dark, highly magnetized regions on the solar surface. Astronomers have literally been counting these things since the invention of the telescope back in the 17th century. More spots? That means more solar activity and violent space weather. Fewer spots means a quiet sun. But what is actually driving this 11-year heartbeat in the first place?
Well, the engine behind this is something called the Babcock-Leighton mechanism. And hey, I know it sounds like heavy physics jargon, but just think of the sun's magnetic field at its absolute quietest point, the solar minimum, as a little seed. As the sun rotates, its equator spins faster than its poles, which stretches and twists this magnetic seed field. Eventually, it gets so tightly twisted that it just bursts right through the surface, creating sunspots. When those sunspots decay, their magnetic remnants are swept back to the poles, essentially planting the seed for the very next 11-year cycle. So, the crucial takeaway here is if we can measure the strength of that seed, we can predict the size of the next cycle's harvest.
Section 2. Two cosmic suspects. The search for the ultimate solar precursor.
Right. So we know we need to measure the sun's magnetic field at its quietest to predict its loudest, but how exactly do we measure it? Astrophysicists generally debate between two primary indicators, or precursors. On one side, we have hemispheric polar flux. This is a super-targeted measurement. It only looks at the magnetic flux clustered right at the sun's high-latitude poles. On the other side, we have the axial dipole moment. This one takes a much more global view. It measures the radial magnetic field integrated across the entire solar surface, not just the poles. And for a long time, it's been this huge open question in astrophysics. Which of these two is actually the superior predictor?
Now, you might be thinking, well, why don't we just look at the historical data and see which one won in the past? Well, here is the giant roadblock in our investigation. We only have direct, high-quality satellite observations of the global axial dipole moment starting from solar cycle 21. That is just 4 solar cycles. 4 data points are nowhere near enough statistical evidence to crown a clear winner in a complex physics debate like this.
Section 3. Testing a century of data. The SBO-TROM simulation.
To get around this massive data drought, researchers deployed a pretty brilliant workaround, a highly advanced data-driven surface flux transport model called SBO-TRAM. They basically fed a century's worth of historical sunspot records into this simulation to reconstruct the sun's magnetic history, all the way back to, well, back to solar cycle 15. And when you plot the simulation against our actual modern observations, they overlap beautifully. By proving the simulation matches modern observations so perfectly, we can completely trust its reconstruction of the past 100 years. So just like that, we went from having 4 measly data points to 10 full solar cycles of data to test our 2 suspects against.
With a whole century of data, we can finally run some deep mathematical diagnostics. When they ran a wavelet coherence analysis, the results showed these deep, highly statistically significant correlations perfectly locked into that 11-year cycle. And the math proves, based on the phase orientation, that both the polar flux and the dipole moment physically lead the sunspot activity. They truly are precursors. But the big question still remains, which one is better?
Section 4. The winning predictor.
The verdict.
Okay, we've interrogated a century of reconstructed solar history, and it's time for the verdict. The paper ran correlation tests across 6 different metrics to see which precursor better predicts the amplitude and rise rate of the next sunspot cycle. And in every single metric, the axial dipole moment completely dominated. It forms a significantly tighter, more reliable correlation than the polar flux. In fact, for predicting the maximum sunspot area based on the minimum phase precursor, the axial dipole moment scores a massive 98.4 to 99.7% correlation reliability. I mean, that is just a stunning statistical victory.
But here is the absolute best part. It doesn't just win on accuracy, it wins on time. The data reveals that the axial dipole moment reaches its peak correlation approximately a full year earlier than the polar flux. In the business of space weather forecasting, getting a highly accurate prediction 12 whole months ahead of the competition, that is an absolute game changer. So why exactly does the global view win out? Well, the physics here is actually incredibly elegant. Polar flux only measures the poles, right? So it has to wait for the magnetic remnants of sunspots to physically travel from the sun's equator all the way up to those high latitudes, and that transit simply takes time. The axial dipole moment, on the other hand, measures the global field. It responds immediately to the emergence and decay of active regions across the whole sun, capturing that magnetic evolution before the flux even reaches the poles. So it is, undeniably, the true primary magnetic precursor.
Section 5. Forecasting Solar Cycle 25, the ultimate test.
All right, we've cracked the code, so let's point this winning model right at our immediate future. But first, let's look at the receipts. If we use the axial dipole moment at the end of a cycle to predict the next one, how well does it actually do? Take cycle 22. The model predicted 2347, and the actual was 2572. For cycle 23, it predicted 1852. Actual was 1833. Crazy close. Cycle 24 predicted 1132. Actual was 1251. The model is incredibly tight. It is highly accurate and totally trustworthy. So what does it say about the cycle we are in right now?
Well, the forecast is crystal clear. Solar cycle 25 is expected to be a significantly stronger cycle than solar cycle 24, meaning we are currently experiencing a much more volatile space weather environment than we did over the entire last decade.
To put some hard numbers on it, the model predicts a peak amplitude ranging anywhere between 123 and 157. And what's really amazing is that as we sit right here in the middle of solar cycle 25 today, the actual observed progression is matching this forecast brilliantly. Recent observations are tracking right at the top edge of this exact range. The model absolutely works.
And timing-wise, the axial dipole moment doesn't just predict the strength, it tells us exactly when we'll hit maximum volatility. The math shows the cycle, which kicked off in 2019, hits its absolute peak between mid-2024 and the very beginning of 2025. So yeah, we are right in the thick of the highest risk window for satellite disruptions and power grid anomalies right now.
To wrap this all up, I want to leave you with the concluding thought straight from the paper itself. This work provides stronger evidence supporting the axial dipole moment as the primary magnetic precursor for solar cycle prediction within the framework of the Babcock-Leighton dynamo mechanism. It's a massive step forward for astrophysics and, honestly, for protecting our entire technology-driven world. We finally found the true signal in the solar noise.
We survived cycle 24, and we're currently navigating the peak of a much stronger cycle 25 with a better map than we've ever had before. But the sun never stops churning, does it? As we watch the dipole moment build over these next few years, the real question is, with the sun's magnetic code finally cracked, what secrets and what kind of crazy space weather will solar cycle 26 reveal to us? Keep your eyes on the stars, and we'll see you in the next explainer.